Hello students. Finally, we will state and prove the sum identities of sine and cosine. We proved all other trigonometric identities. Here we have a summary of all the trigonometric identities that appeared before chapter 7, and we proved every single one of those. Some of them, like Pythagorean identity, we proved multiple times because they're important. I think I did it at least 3 times in chapter 5, in chapter 6, and at the beginning of chapter 7 as a review. Quotient identities, again, I think I did it multiple times. Tangent is sine over cosine. Easy, but important, so we did it multiple times. As for the new identities that showed up in chapter 7, everything was based upon the sum identity of sine and the sum identity of cosine. For instance, how about the difference identities of sine and cosine, like these two? Well, we can deduce those from the sum identity of sine and cosine simply by replacing alpha minus beta by alpha plus of negative beta and applying the sum identity and doing the computation like that or like that. In any case, you can clearly see that everything is coming from these two. How about the sum identity of tangent? Again, we proved it using the sum identities of sine and cosine. Because tangent is sine over cosine, which we already proved, we can write tangent of alpha plus beta as this over that. And then divide both numerator and denominator by cosine of alpha times cosine of beta, and some simplification, we get what we want. And applying alpha minus beta equals alpha plus negative beta, again, we're going to get the difference identity for tangent as well. The other identities, they're all coming from the basic sum identities for sine and cosine. How about the double angle identity? Just apply the sum identity as theta plus theta. Same for cosine, just theta plus theta. And then we can use Pythagorean identity to re-express this result into this and that. But still, we have proved everything. We used Pythagorean identity, but we proved it early on. The only thing that we are still using without proof is this one and that one. And double angle identities gave us the power reduction identities simply by solving for cosine squared from here and sine squared from there. And changing theta into half of theta, we get half angle identities. Sum to product, product to sum, those are all coming from the sum and difference identities of sine and cosine. For instance, alpha is half of alpha plus beta plus half of alpha minus beta, and beta is half of alpha plus beta minus half of alpha minus beta. So we have these 4 different types of sum and difference identities of sine and cosine. Taking appropriate pairs and solving, we're going to get, well, all these 4 formulae. Similar thing applies for product to sum. We begin from the sum and difference identities of sine and cosine, as before, and then take appropriate pairs, add and subtract to solve, and you're gonna get these 4 formulae. Triple angle identities, those are a little bit harder cases, but still you can see that everything is based upon the sum identity, theta plus 2 theta, and then double angle identities, and then Pythagorean identity. It's difficult, yes, but still I think it is clear that everything is coming from the sum identity of sine and cosine, along with some other trig identities which are already proved. In short, the only trig identity that is yet to be proven is the sum and difference identity of sine and cosine, which we're going to do now. This one and that one. Okay, how do we prove it? We're going to take a bit of a digression to do that. We're going to talk about the rotation in plane first, and there's a reason for that. We're going a little bit deeper than the way it is written in our textbook, to be sure, because our textbook does not really deal with rotation in plane, at least in a full detail. The reason we are going deeper than our textbook is because this digression is by itself very, very important, especially if you move over to higher level math course. Most typically Math 2700, linear algebra, and then of course hordes of other courses too, like 3410 differential equations, 2730 multivariable calculus to a certain degree at least, and then Math 3000 real analysis 1, and so on and so forth. I mean, and the list goes on actually. In any case, here's a formula. Here's a visualization. We begin with x comma y and take the rotation by angle theta, and we get capital X comma capital Y. And this new point, capital X comma capital Y, can be represented by this: x cosine of theta minus y sine of theta, and y is x sine of theta plus y cosine of theta. This is by itself an important application of trigonometry, and we're going to prove that. Let's do it. One way to prove this, one way to visualize this, is not just looking at these 2 points, x comma y and capital X comma capital Y. Follow these 2 triangles. We have a right triangle in the left hand side, and we have another right triangle in the right hand side, but those 2 are the same triangle, just tilted, just rotated by the angle theta. Horizontal is x, vertical is y, and as you can see, yes, the same right triangle. Now, what we are going to do is to use the coordinate of this blue point of the second picture, the right hand side picture, as an intermediate step to find out capital X comma capital Y. So keep this second picture, the right hand side picture, in your mind. Okay. Now, how do we find out capital X and capital Y? Let's find out capital X first. Here's a visualization. What we do is to draw a vertical line from that blue point, yes, intermediate point, this blue point of this second picture, and create this blue right triangle. And please note that X is hypotenuse. So the horizontal of this blue triangle is x cosine of theta. That's the x coordinate of this blue point. And now, let's go over to the fourth picture, the right hand side picture. We do something similar this time, but we're going to do that to this red triangle. Here, we have the same right triangle with same angles, but size is a little bit different. Hypotenuse is this time y. So horizontal in this case is y sine of theta, because theta is top angle. So what we have, we can find out the x coordinate of this capital X comma y, or capital X value. X cosine of theta, coming from the first picture, and subtract away y sine of theta from the second picture here. And consequently we have this: x cosine of theta minus y sine of theta. And please note the color coding. That's where, well, I mean x cosine of theta is blue because it's coming from the blue triangle, and y sine of theta is red because it's coming from the red triangle, the second picture. Let's go back. We are looking for capital X comma capital Y, yes, eventually this one, and rewrite those using the intermediate point, this blue point, and we use a couple of right angle trigonometry to figure out the blue point and the relationship between blue and the ultimate point, capital X. We get cosine x cosine of theta minus y sine of theta. We can do something similar to the y coordinate, capital Y. Here we go. We are looking for capital Y. So this time, let's draw a horizontal line from this blue intermediate point and get this blue triangle. From this blue right triangle, you can see vertical is x sine of theta because x is the hypotenuse. Now we have to go up a little bit further to reach capital Y. So what do we look at? We look at that red triangle in the right hand side. Hypotenuse is this time y, so the vertical is y sine of theta. And by adding those two up, you're going to get capital Y. That's how we get this result. Capital Y is x sine of theta plus y cosine of theta. And that completes the proof. And here we go. If you have rotation, then we have this formula. Okay. By itself, this was a nice result because we just learned rotation. Well, we learned translation with respect to the x-axis and y-axis, and the flipping, magnification, stretching, compressing, all those in college algebra. Rotation we didn't, but we just did. But we are going to use this rotation to prove the addition theorem for sine and cosine. How do we do that? Here is the mechanism. This is what we are going to do. Start from 1, 0 and then take the rotation of angle alpha to get small x, small y. And then the rotation of angle beta to get capital X, capital Y, as you can see in this first picture in the left hand side. And I did a color coding. Alpha is blue and then beta is red. Now, if you look at the second picture, just take the rotation from 1, 0 all the way to x, y, capital X, capital Y, by taking the rotation alpha plus beta all the way. These two results have to be the same because we are looking at the same point on a circle. Alright, if you look at the right hand side, it's going to be related to angle alpha plus beta. If you look at the left hand side, it will be related to alpha and then beta separately. So how do they work? Works like this. Let's see. You can see everything in a single viewing window, barely. Okay. Now we start from 1, 0 and apply the rotation with respect to the origin by the angle alpha. So in this case, take theta equals alpha, and then x, y will be 1, 0, and you're gonna get cosine of alpha, sine of beta. You get cosine of alpha, sine of beta because it's the terminal point of this blue arc, but you can use rotation to understand that. Anyway, this blue point here is cosine of alpha, sine of beta. I think this is just confusing you with x and y showing up again. Now, from x, y, the blue point, we take a little bit more rotation by the angle beta. And that's where we're going to use this rotation. X cosine of theta, y sine of theta, x sine of theta, y cosine of theta, like that. So x cosine of beta minus y sine of beta because the angle is beta. And then x sine of beta plus y cosine of beta because the angle is beta. But please recall that x is equal to cosine of alpha and y is equal to sine of alpha. So what do we get? Capital X is equivalent to cosine of alpha, cosine of beta minus sine of alpha, sine of beta. Capital Y, on the other hand, is the same as cosine of alpha, sine of beta plus sine of alpha, cosine of beta. Now let's compare that result, the red one, into the green one. This time we have cosine of alpha plus beta, sine of alpha plus beta. So cosine of alpha plus beta has to be the same as cosine of alpha, cosine of beta minus sine of alpha times sine of beta, which is precisely what we wanted to prove. And comparing the second coordinate, we get sine of alpha plus beta is equal to cosine of alpha sine of beta plus sine of alpha plus cosine of beta. Is that the same thing as what we wanted to prove? Yes, indeed, because addition and multiplication are just commutative. Sine of alpha cosine of beta plus cosine of alpha times sine of beta is the same as this one. That completes the proof of the sum identity of sine and cosine.